So let's go for the example. Okay, so in this example, we have the simplest case that we can have for a wing spar. All right, so I'm sure you can do better than me. So there is two flanges or two stiffeners. So this will be here the panel. All right. This one is subjected to just a downward vertical load of 20 kilonewtons. The total length of this part is 2 meters. Oh, then we have to be careful here. Maybe not. We can change this easily. If you want, at the root over here, it will be 1.4 meters. At the tip, it will be 0.2 meters. Okay, the question here is that if we make a cut in the middle, let's say we make a cut at section AA, which is located right in the middle. So let's say this would be 1 meter. They ask us to determine the shear flow distribution in the panel assuming that the panel is fully effective in resisting bending stresses. So basically, the other day we studied two cases. We said one, that the panel wasn't going to be effective in resisting bending shear, and the other one, bending stresses, and the other one that yes. So this case is case 2. The other day, class notes. And if you go back, we had that PZ1 was equal to the stress at 1 times boom area 1. PZ2 equals sigma C2 B2. Okay, so this comes from the notes the other day. If we do the idealization, basically this will mean this is B1, 2, Okay, this would be here the thickness. I forgot to put some data over here. Let me just put it over here on top. Can you see that? Yes. So B1 will be equal to B2. And this is equal to this in millimeter square. I have to change everything to millimeters. And that the thickness of the panel is 2 millimeters.
So like B1, like that's the total area of flange one.
Yes, correct. This would be, this is the idealization of the flange one, this is the idealization of flange two. Okay. And I'm going to put some more data here. Since B1 and B2 are equal, we will be located in the neutral axis. Right in the middle, no? Here's from where we calculate the y's over here. Okay, so over here, let's first calculate that loading at the cut. So since we are dealing with bending stresses, what do we need to find? Bending is induced by what type of load? Bending moments, no? Okay, so at the cut, what will be the moment? The value of the force times the distance. So in this case, it would be equal to what? What is the force? 20 kilonewtons times 1 meter. So this will give us M equal to 20 kilonewtons per meter. Okay, and this is not, we don't need it for the problem, but just for the understanding, let's say, if you needed to do the figure of the, so let's say this is Y, this is X, so let me call this MX then, okay? That way this will be Z, Y, X. The bending moment diagram look like? If something is cantilever, what will be the maximum moment? What will be the maximum moment? At the edge, and what should be the moment at the free end? 0. So if we do it, would be something like this, okay? And we are right here. So it would be the total moment. But for us, we are right here, okay? So what should be the moment over here? It would be the 20 kilonewton times 2, no? 40. All right, so, and here would be M 0, M 40, M 20. Okay, the expression for the bending stresses, let me put it over here. The general form will be what? Mx times y divided by x. That will be the bending stress. So in order to calculate this, we calculated the moment, which will be 20 kilonewtons per meter. We need to find what will be the moment of inertia, and y should be equal to what? Should be just be equal to the half of the height at this section, no? At the cut. So let's first find what is Ixx. So let's say moment of inertia. Okay, so moment of inertia. Let me do the boom over here again. This is B1. This is B2. Let's say this is H. This is T over here. Okay, so from the previous page, we know that B1 equal B2 equal to 400 millimeters squared. And that T was equal to 2 millimeters. So it might just be easier to work in millimeters. So let's see. This is pretty simple. So if the height over here is 0.4 or 400 millimeters, and at the tip is 200 millimeters, and this is a linear, what should be the height at the cut? Should be 3. So that means here we're gonna have H equal to 300 millimeters. So 0.3 meters or 300 millimeters. But since everything is millimeters, I want to change that. And again, we can say that our neutral axis from the figure before will be right in the middle. And from here is from where we're going to calculate dy. So the total moment of inertia is going to be equal to what? It's going to be equal, let's say, to the moment of inertia. Because this one prime, which this one will be two flanges or stiffness. Plus, in this case, since this is case 2, what does that mean? We're also going to have a moment of inertia. Due to the panel. So let's do first the one. Oops. First the one of the panel. This is just one. What should be equal to the moment of inertia? Generally is equal to what? dA. So Ixx, sorry, prime. But we say that this can be approximated by what? The summation of the B sub r's actually I did a mistake here. This should be y squared dA. I was thinking about the Q, yr squared. And this will be, so it should be equal to what? B1 y1 squared plus B2 y2 squared. So this should be equal to what? What is B1? 400. What is y1? Is the distance from the neutral axis to the top, no? So how much would that be? Half of h, which will be 150, or if you want, but so y sub 1, if you want here, but h divided by 2, 150, y sub 2 minus h divided by 2 minus 150. And this one will be plus 400, I forgot the square, times minus 150 square. So if you do the calculation, you get the I prime x double x. So due to the flanges is equal to 18 10 to the 6 millimeters to the 4th. Okay, so this is a contribution of the only the flanges. Now we're going to look at what will be the contribution of the panel. So what should be the contribution of the panel? Would be 112. What is the base over here? This is the panel here, no? So what will be the base? T. And what will be the height? Okay, would be no, would be the whole thing, no? So H cube. Let me put something here, maybe so some of your faces were not that clear. This is A, this is B. I is equal to what? 112 A B cube, no? This is our T over here. The A is the T. So that means that here we're gonna have 112 times 2 times 300 cube. And if you do the calculation, this is gonna give you I double prime XX equal to 4.5 10 to the 6 millimeters to the 4th. Okay, so that the total moment of inertia would be equal to 22.5 10 to the 6 millimeters to the 4th. Okay, so out of this equation here that we had initially, we know M, we know the moment of inertia, and we know Y, no? So now we can calculate this expression here to calculate what is the actual load on the, what is the PC component of the actual load on each one of the flanges. All right. So from here we can calculate sigma Z1 would be equal to mx y sub 1 over ixx, and sigma Z sub 2 would be equal to m sub x y of 2 over I XX. Okay, so here, be careful a bit with the units because what do we have? Maybe we need to do this in 2 steps. This is what, 20 kilonewtons per meter. Y, we say was equal to what? $150 millimeters divided by the 22.5, then to the 6 millimeters to the 4th. So what do we need to do with this term?
millimeters.
Correct. So let's say we need to multiply, let's say, to first to newtons and 2 millimeters, no? Okay. And if you do this calculation, you're gonna get over here 133.3 newtons per millimeter square. Okay, we do the same thing for the other one. So we get that negative. Here, I want to stop for 1 second because in this case, it is working, but I would like to get this size over here just from the map, all right? So, next page, let's see what happens. So in this case over here, you agree that I could just model this one very simply, if I needed to model. I could say, this is our beam. And it's going to deform this way, no? Yeah? Okay. So if it is deforming this way, and this is modelized, idealized by this, I think the important part here is the understanding, not that the equation is working. All right, so this is bending this way down. The top of the cross section will be in tension or compression. So this side will be in tension. And tension generally is what? Positive. Okay, and obviously the bottom will be in compression, and this will be negative, no? So in this case, it did work out, but please don't put the sign of this just based on the sign of the Y. Okay, think about a second to know if it's tension or compression, no? Yes? Okay. So the question here is base sign on tension and compression. Not the equation, okay? Okay, so why are we doing all this stuff? Is because if the flanges and the skin are effective, we had case 2, so we can find what would be the Z component of the actual load. So now we can write PZ1 will be equal to the bending stress at 1 times boom area 1. And that PZ2 will be equal to the bending stress at 2 times B2. So we apply this. What do we have for the bending stress? We have 133.3 newtons per millimeter square times B1, which is 400 millimeter square. So if you do this calculation, this is going to give you 53,200 newtons. We do the same thing for the PZ2. Usually this would be minus 53, 200 newtons. But again, I'm not crazy about basing all this stuff about the signs, okay? So basically that means that this is positive. What does that mean about, I mean, this is the Z, it's not the P1. So we'll see what happens next. All right, so if we go again to the case 2, so from the previous notes, if you go back to the lecture, we had that then PY1 will be equal to PZ1 tangent alpha 1. Can do maybe a figure over here. So we have here P1. We are here PZ1. We had over here PY1, and this was the alpha 1. Okay, you remember from the other day. Okay, and similarly, you could write PY2 equal to PZ2 tangent alpha 2. Remember, I said you could write this at PZ1 change in Y sub 1 delta Z1 PZ2 delta Y2 delta Z2. I'll do a figure now so that you understand. So basically, what are we looking at here? We are looking at what is the angle between the flange and the vertical, no? Okay, for each one of them. But instead of using angles, we can use what is the change of slope per unit length for each one of these flanges. Let me do a figure, so it's easier. So hopefully that would be good enough. Two. Okay, so here we need to be careful. So what was the total height over here? What did we have at the roots? We had 4 meters, which is 400 millimeters, no? Yeah. Or if this is, I could say this is 400, I could say this is 200. This is 200. And I could say this is 100. Or this is 100. Or if I look at the cut, what will be this distance here? Will be 150, 150, no? Okay. So basically, we could call this one be our delta y, because it's a change of slope from here to here. And now our delta z can be multiple ones. So let's see. So let's say this will be 1,000. 1,000. But this could also be our delta z, okay, for now. Or it could be, we could use what? This one to be 2,000, and this also could be our delta z, okay? I think you will understand now. So basically we could use tangent alpha 1 is going to be equal to the change in height per the run. So let's see, if we want to calculate the slope of this curve over here, what are the options that we have? We could calculate it from this end to the other end, no? So we could say this is equal to what? Good. Minus 100, no? And what is the run or the delta z for that distance? 2000. But again, since the slope is constant everywhere, we could decide to calculate this from this point to this point, no? Then what would that be? Or you could do 200 minus 150. But in this case, what would be the delta z? Will be 1000. Yeah, and if you want to be even more extreme, we could decide to calculate it from the tip, and this would be what now? 150 minus 100 divided by 1000. But in any case, we're going to get all the time the same result, no? Okay, so you do this calculation, this gives you 50 over 1000, which is 1 over 20, which is 0.05. Yes, that's fine. There we go. Okay. So all this stuff is to substitute over here to find PY1. Okay, so we say now substituting back into the expression that we had before, P Y1 would be equal to P Z1 delta Y delta Z, or 1, whatever you want. This is going to give us 53,000. What was the value? Oh, hold on 1 second. What did I give you before? 53,200. Can somebody, do you have a calculator here?
Yeah.
Are you checking the values?
No, I haven't, but I can.
No, but before, how much was this one here? The 400 and 133.3? Is that correct? Or is it 320?
It's 320, yeah.
So,
320.
so this should be 53, 320, no?
Yes.
You see? 320. 320. Thank you for checking. So now if we do this calculation here, this would be 53, 320 times 0.05 or 1 over 20. What do you get?
36.
How much?
2666.
Okay, 2666 Newton. And if we do PY2, we get PZ2 delta Y sub 2 delta Z sub 2 equal to 53, 320. So actually this one was negative, but again, I don't like the negative or positive signs for this. Would be equal to negative 2,666 newtons. Again, I don't like the positive and negatives, but it's better to do it because sometimes they work, sometimes if they don't work, then it's difficult to find out. Okay, so because of the deformation, now we know that P1 is equal to Py1 squared plus P Z1 squared. 2 will be equal to P Y2 squared plus P Z2 square root. And if you can get some values, that would be great. You have the values? You have the values or no? Working on it?
Yeah, 3,386.6.
53,000?
386.6.
Yeah, about the same. Now they should be about the same. Those values are not that important, but just to know this stuff. So if it's an intention, they're on this form, and if there are compression, they will be on the other form. Okay, so after doing this, if you go to the notes from last class, we can find what is the shear force in the panel. Okay, so that's where, again, we need to do another figure. Maybe I go one more on top, one more at the bottom. Okay, so maybe let's do a small figure here. I don't know. Okay, let's do it here. If we do the shear diagram, I mean, this is not needed, I'm just giving extra details, but if we look at this figure here, what should be the same thing we did here, the bending moment diagram, we can do the shear diagram. What will be the force going down throughout the whole section? It would be 20, no? Yeah, so it would be the same everywhere on the cut. We have here, this will be 20 kilonewtons. Okay, you can decide to make it up or down, whatever you want. Okay, so let's look at this. So let's say I make it going. You want me to make this one going up or down? It should be the 20, no? Okay, all right, so let's say it will be 20 kilonewtons, and this is due to our external force, no? External actions. I think this is the easiest way to do this. And that way you don't have to worry about too many signs or anything. Okay, what is going to resist this force inside the for the structure? Which elements are going to resist the external force? Oh, no. Yeah, you could say here, so it doesn't matter which way you do it. That's what I'm saying. To me, it doesn't matter which way you do it. I would just say everything up on the opposite direction would be V. Sorry, I will call this one P. This should be what? P Y1. This should be P Y2, correct? And then over here, it should be a V. I think I call it V panel, no? The last notes. Please check because I change sometimes. Yeah, did I use VP on the last lecture? Please go and check. I don't want to change the notation. Yeah, you did. Okay, good. So basically, I think the best way to say is that this will be all internal action. So let's say I could say here, all the external forces need to be resisted by all the internal forces, no? And let's forget about the signs. That way would be, I think it's a lot easier. So what is applied externally? So will be the 20 kilonewtons. Be resisted by what? Py sub 1 plus Py sub 2 plus the shear in the panel. Okay. Okay, so now we can say, and this is where it gets, I mean, that's where sometimes people do a mistake. So V on the panel will be equal to what? Whatever is X. So whatever is not being resisted basically by the vertical components of the shear force in the flanges. Yes? Okay, so that's why I don't like to put signs. So now, VP really should be equal to what? 20 kilonewtons minus what? What is Py sub 1? 2,666, no? Yes? 2,666 minus what should be P2, Py2. But no, you see what happened? You put negative, then what's going to happen? It's going to switch the sign and it's not going to do anything. But that's what I'm saying here. Physically, what we need to understand is not negative. We are seeing these two resisting the external force, no? So we should only be looking at the magnitudes. You understand this part? That's why really I don't like to put signs. If you ask me here, I will not put signs. I will remove here these signs and put. That won't make sense. Okay, I will put here tension and here compression, no? So in here should be minus 2,666. Do you understand what I'm doing over here? I'm forgetting about using the logic, the common sense. So now if you do this calculation, the V the shear force carried by the panel will be whatever, I think it's 14,668 Newton. Okay, now that we have the shear in the panel, we can calculate what will be the shear flow in the panels. So now we can say the shear flows Q sub S in the panel is given by what? The equation we have been using all the time, minus V panel. In this case, we only have one, IXX. But if you remember, because this time the panel is effective, we have Y TDS. I think this should be the summations, but plus B sub I, Y sub I. And this will be the shear due on the flanges, this is on the panel. So here we go, let's do more figures. B1, B2. Natural axis. Okay, so remember at the cut we have H equal to 300 and T equal to 2 millimeters. So now this is the part that generally is hard. Y is always calculated from the natural axis, but when we calculate the shear, we start from one location. So for instance, over here, what do we have? It will be Q, 1, 2 of S in that direction. Will be equal to what? What is VP? Minus 14,000. That's not that important, the direction, we can change it, but how much was this? 14,668 divided by IXX, which is 22.15 to the 6 times integral. So what is the distance over here? That was at the cut. Remember here we had the cut, no? Where are we here? We are, where is that page? We are here at the cut. That is calculation being done at the cut, no? So it's 150, 150. All right, so this is from 2 lectures ago. What will be then the y over here if we start from the top? Let me write it down and then maybe the y would be 150 minus s, no? It's going to 0. Okay, so this will be our y's, this y over here at the top. T we know is 2 millimeters. So we go from 1 to 2. So that will be this. What is B1? Maybe I should put that in red, but it doesn't matter. This will be B1. And what is Y sub 1? $150. So if you integrate this, you see this is in function of S. I give you the value. This gives you minus 6.52 10 to the minus 4. Times minus S squared plus 300S plus 60,000. Okay, I give you here some values. You don't need to calculate, but basically Q12 at 0 should be equal to what? Gives you 39.14, and Q12 at 150, which would be the maximum value, would be 53.8. So if you look here at what's happening at the cut, let me do it over here. Let's say this will be B1, B2. This will be here our natural axis. What you get over here is a distribution that should be here 39.14, and the maximum will be 53.8. So I think the other day I give you a FIMAP code, no? For video. All right, so let me try to find it here. But it is not going to be that accurate because if I remember right, the mesh was not that good. I'm not sure if I'm opening the good one or not. Okay, yeah, I think I opened the good one. So basically, I think I showed you the video. Obviously, you will get much better results. Oops, why is it not showing? That's strange. Oh, here we go. Okay, we're over here. You see that if we're making the cut, if you do more cuts, you will probably get closer to the 53, no? Okay, but again, it's hard for me to do this. I think you need to go here to groups and save you all so you can see the whole thing. All right. So then there's case two. We're probably gonna say, sorry, case one, but we're probably gonna do that one next time, so we have time to talk about what is gonna be on the exam on Thursday. Any question about what we have done today? All right, so let me stop the video.